Hello everyone, my name is Tarvi Tamm and today I will be presenting a research paper review titled Enhancing Diagnosis Ensemble Deep Learning Model for Fracture Detection Using X-ray Images. Bone fractures are one of the most common medical conditions worldwide, but their detection is still heavily dependent on radiologists manually interpreting the X-ray images, and the manual fracture diagnosis is slow and error prone. And the solution for that comes with artificial intelligence as a powerful tool to then assist radiologists. Deep learning, in particular, convolutional neural networks, can automatically learn patterns from large image datasets, helping detect fractures faster and potentially with higher accuracy. And this study specifically investigates how ensemble deep learning, which basically combines multiple neural networks, can further enhance diagnostic performance. This paper is directly relevant also to our project because our project also focuses on automated bone fracture detection, while our project explores different classical machine learning and deep learning techniques. Then this paper adds a new dimension to it by applying ensemble learning and providing another perspective on the problem. And both this research paper and our project also share the same goals and challenges. They aim to reduce misdiagnosis and they improve clinical decision support, and also a big emphasis on the sensitivity as a key metric to minimize missed fractures. The dataset in this research paper focused on the Mura 1.1 dataset, and from that dataset, the research paper authors took only a subset of X-ray images, focusing on the humerus. In total, the used dataset for this ensemble deep learning approach consisted of 6,542 images, and the pre-processing steps included histogram equalizations and different data augmentations like rotations, flips, zooms, in order to generalize the model more. And the model that they used, the ensemble model, used a stacking algorithm. And here on the right-hand side, you can see the proposed ensemble model pipeline on how it works, but more about the model architecture on the next slide. The idea was then to combine multiple convolutional neural network architectures into an ensemble to improve the classification robustness. Each of these architectures contributes unique strengths to the overall system. And starting with the VGG16, one of the earliest deep convolutional neural networks, and it is known for its simplicity and uniform 3x3 convolutional layers, which basically provide a strong baseline for image classification tasks. Secondly, ResNet 50, which introduces residual connections, which help overcome the vanishing gradient problem and enable much deeper networks to train more effectively. Thirdly, the MobileNet V2, which is optimized for efficiency and has a low computational cost. It uses depth-wise separable convolutions to achieve higher accuracy with far fewer parameters, making it also lightweight and suitable for fast inference. And finally, the Inception version 3 uses multiple convolutional kernels of different sizes in parallel, allowing it to capture both local and global features at various scales. Although its weaknesses is that it is very complex and the inference is very slow. After training each of these models individually, the authors combine their outputs into an ensemble model that aggregates predictions from all 4 networks. And this ensemble approach helps reduce individual model bias and improves the system's robustness. And from the results, we can see that the ensemble proposed model outperforms all individual convolutional neural networks by roughly 2 to 3%. Specifically, the ensemble reached an accuracy of 92% with strong precision and recall values also across the test set. There was a major recall improvement, especially if you compare it with the first 3 models, basically meaning that fewer fractures were missed. And yeah, as I said, this ensemble model helps capture different visual patterns and reduces the model bias and makes the fracture detection more robust. The strengths of this approach are definitely the complementary learning, as we saw also on the last slide, that overall metrics increased by using this ensemble approach. The use of pre-processing and augmentation that the research paper authors did reduces overfitting, and they also used consistent evaluation metrics such as accuracy, F1, and recall. The weaknesses, in my opinion, there were quite a few. The data set, first of all, it was pretty small, consisting of only 6,500 images, and it was limited to only one anatomical region of the human body, which can lead to a poor generalization, meaning that this trained model will not perform as well on different parts of the body. The approach used no cross-validation. There was no validation set. It was just a single 80 to 20 train test split, which risks the bias of the model. Also, since this approach would be used in real time, then the model complexity and computational cost is also definitely one of the factors that we have to consider, as combining these 4 models will add a lot to the complexity and inference running time as well. There was no external validation or computational analysis. It was just done on their own test set. I think by having a totally different test set to further test their own model, it would have been nicer. All of these models had a training time of 8 epochs, which may undertrain deeper convolutional neural networks. So when training the models, then adding more parameters which allow for longer training would, I think, in my opinion, also raise the performance of the model. And finally, there was no statistical significance testing. The overall assessment, I would say that this paper demonstrates the power of ensemble learning, shows its heavy computational load, which could also be a bottleneck for real-time use, as I previously mentioned. And yes, I think for validation, and to claim generalizability, it needs testing on external data to actually see how well it performs. in a different environment. And future works for things that would possibly be good areas to focus on. First, the explainability and trust to visualize the predictions and where these performance metrics numbers actually came from, what are the edge cases of the predictions, and yeah, which regions influence the prediction the most. Then, as I mentioned quite a few times already, the external validation to ensure the robustness and reduce the dataset bias. Thirdly, because this approach only focused on classification, then it could also be modified so that it could also do object detection, so localization alongside the ensemble classification. Although the Mura dataset that they used only allowed for classification, since it didn't have any annotations with, for example, bounding boxes. It only had the classification label, whether it was a fracture or a normal image. And finally, to also do model efficiency analysis to potentially reduce the complexity of the proposed model. So all in all, it was a technically strong ensemble learning approach, achieved higher accuracy and recall, which in themselves reduce the risk of misdiagnosis. The model had a high computational cost and lacked external validation, and all in all, it provided a valuable insight into the strengths and weaknesses of ensemble learnings, and definitely a few key points that we can also take into our own project going forwards. Yeah, all in all, the study demonstrates that with ensemble deep learning, it can enhance diagnostic accuracy, but the true impact requires models that are interpretable, efficient, and validated across different diverse data sets. And these are the references that I used in addition to the paper itself to familiarize myself more in the topic. And yeah, that is it from my side. Thank you for listening.